Thank you for joining us today for our webinar that we're doing on the permanent partial discharge monitoring of transmission-based assets. Joining me today is Brodie Ward from Powerlink, Queensland, and I'm Thomas White from EA Technology. So what we're going to be presenting today is one of our joint projects that we've been working on for a couple of years together, of where we're trialling the permanent monitoring of transmission-based assets in outdoor yards and seeing how they can apply in a transmission company's team and seeing how well it works for them. These particular projects were done as part of a EIC paper that Brodie and I wrote and we submitted and presented back in 2022. So what we're going to go through with you today has been published and is available, and you'll also get an article sent out after this webinar going through all of the findings. So what we're going to go through today is a little bit of the background about the project at first and how it fit into Powerlink's regime and how they used it internally. From there, I'm going to explain to you how we actually physically did the monitoring outdoors and what hardware we used, and then how we did all of the analysis. Then Brodie will take over and run through the full failure and the dissection of what we looked at and the end results of what we were doing. And then we'll finally finish with questions. So the full background of this project started in 2020. Powerlink and EA Technology formed a partnership to explore the benefits of moving our well-documented partial discharge monitoring from switch rooms and on switchgear and moving it out to switch yards and using them for outdoor assets. In the project, we originally picked 3 main monitoring sites. But the one we're going to be talking about today was 6 oil-filled 275 kV cable terminations that were installed in 1996. These cable terminations were originally identified as during Powerlink's regularly scheduled maintenance regime. They were found to have poor DGA results, which flagged it, and they wanted to do a bit more investigation. This program of the permanent discharge monitoring started on the 1st of the 10th, 2020, and we monitored for a number of months moving forward. We analysed all of the data, provided real-time feedback to Powerlink, who could then make the right decisions. The 17th, the 11th, so a little bit over a month later, Powerlink was actually able to de-energise these assets where the poor results were from. We were able to narrow it down to a single termination, and we did a full forensics breakdown. On the right there, you can actually see a bit of a sneak preview of what we found once we took the terminations apart. So this is the abstract, and this is what everything came from. So this was submitted and accepted, and it runs through. If you are interested in reading the formal paper, you can get in contact with us, and you can. It is available for everyone online. But when we talk about partial discharge monitoring and the benefits of it, we kind of come at it from 2 different aspects. You've got your operational aspect and your asset managers. And Brodie will talk a bit more about how this fit in with Powerlink, but from my point of view and EA's point of view, we break it down for these reasons because operationally, the biggest one is safety. With electrical assets, and especially ones that do have that inherent risk of failure or moving towards end of life, the more we know about them and getting that real-time data allows us to improve safety for the workers. For this particular zone, due to the levels that we're seeing, there was restricted access put on it, so Powerlink had a little bit more difficulty getting close to do other forms of tests like your DGAs and everything. So the more data that we could have coming remotely allowed them to make the best decisions. From there, you can move to your asset management side. The people needing the right data to make the right calls. Because for Powerlink and a lot of asset owners, the decision to turn off this level of asset is not something that can be taken lightly. So I'll pass over to Brodie to have a bit of a chat from the Powerlink point of view.
Absolutely. So this technology was used in a real-world application. So you can see in the image there 2 side-by-side 3-phase 275 kV oil terminations. In the process of our normal routine maintenance, we know that these terminations were in an aged condition. We did know that there was presence of acetylene in the dissolved gas analysis, which leads towards internal activity that's undesirable in electrical assets. And we wanted to ensure that if people were to work around these assets, that we have the most up-to-date information to dynamically make not only operational decisions, but whether or not that environment is safe for our people. It's important to note that this supplies a critical load center. So just an outage of both or a single circuit has impacts throughout the network. And as far as that goes, it was very hard to take outages. So we had to look at other solutions, which is when EA Technology and Powerlink formed this project to better understand how the monitoring is conducted in a live environment with live operational data, and to provide that confidence to operations and our field staff to provide early warning systems for impending failure of HV assets.
I will say a couple of people are having audio issues. It does seem to be good on the whole, but you can try logging in and out if it does persist. So when we start to look at partial discharge in outdoor yards, there are a couple of things we have to take into account. So there are three main types of partial discharge, and anyone who has done a lot of testing would be very familiar with this. So one of the big three is internal discharge, and that's when you have a void or a discharge effect happening trapped within insulation. You then have problems like surface discharge, which is your electrical training, and it's discharge occurring on the outside of your insulation. And then you've got a massive and very prevalent one in outdoor yards, which is corona discharge, is when you've got a discharge occurring at a sharp point, discharging out to the air. And the reason that this becomes so prevalent is you have to also consider what are the failure modes we are looking for. Within the terminations we're looking for, one of the things that we discussed at length is that the types of test methods we do have to follow the types of failure modes we're looking for. So traditionally, internal type discharges are found using the TEV method, the transient earth voltage method. Surface discharge and corona are primarily found using ultrasonic type testing. But when we did discuss the type of failures and the type of things we're trying to look for and prevent, we discussed really that it's going to be primarily those internal type discharges. It's going to be problems going on within the oil or within sealed insulation that we cannot easily ultrasonically test. And that's why when we do talk about the hardware itself, you will start to see that we primarily focused on the TEV method.
It's important to note that when we were discussing what type of technology we would use, we trialed several different methods. So using the PD Hawk, which is predominantly UHF, to the transient earth method as well as the acoustic. So it's important to use all those different methods to narrow down what's the best solution for your asset.
And one thing where it did come from is Powerlink has been a very big adopter of UHF testing. It's something that in their field testing and their day-to-day hand testing, that's what they use quite predominantly. But for the monitoring, it wasn't as viable, so we chose to go with another method. And I'll talk about why we did that in a second. Where it does get a little bit more complicated in outdoor yards is the more tricky types of discharge, things like your contact types and small spark gaps where they're discharging, because that is very prevalent in outdoor yards. So when we're working with this project, we actually needed to have a way where we could distinguish between all of the discharges and switches or the corona discharge and all the little things which are quite common and not necessarily a problem. And we had to kind of disassociate that from the true internal void problems which we thought may have been leading to a failure. And that came with its own challenges. So as I said, we would traditionally use ultrasonic TEV and UHF, but for this trial we did TEV only. And the way that we made that viable with the monitoring system is by using time of flight. So we were able to put TEV sensors on as many structures as possible. You can see one mounted to the bottom of the CT there on the right. And then all of those sensors talk to each other, and they did time of flight so we could establish where the signals were coming from. To take that a step further, we actually started to put TEV sensors on surrounding structures at times, which allowed us to distinguish if signals were coming from further assets further down the line, or if they were originating from the assets we were looking to test. This, if you really wanted to, could actually be extended quite far. If you wanted to do a large number of sensors on every single asset, you can actually really narrow down the data and get really good data for just the ones you're looking at. But for this project, because we were more concentrated on very specific assets, we just monitored those and an asset on either side to get that kind of aerial setup. And that's where we also started to use the phase plot analysis, which I'll talk about a lot. So how do we do it? And it's one of the hardest things. Anyone that has worked with EA for a while would know our UltraTev range. And we have a line of monitoring systems that is very well suited and very well proven for indoor boards. But taking those structure, that system, and moving it outside, especially in far north Queensland, where this was based, posed a number of quite tricky scenarios. They had to be very well rated, very well waterproofed. And what we ended up creating, you can see there in the picture of the yard in the middle, is we waterproofed our nodes and we created fully embedded waterproof sensors which stood the test of time. During this particular project, Powerlink actually designed their own mounting case for the hub units, the hardware and the servers. And since then, EA has actually adopted that and we've created one of our own. And you can see a mock-up of it there on the right. So doing this and getting it to the waterproof was actually one of our main hurdles. With the sensors themselves have been proven and worked quite well, but taking them outdoors, especially in Queensland, was quite a challenge.
A testament to that is that the nodes you see there were photos taken in 2020.
Yep.
And those nodes are still currently operating.
Yeah, I think you still have the 3 working out in site. One of the next things we did is, obviously we talked about these were restricted zones because of the high levels of oil, acetylene in the oil and some other tests. They didn't want people having to go and inspect these or test them physically. So all of the data came back to us in the cloud. And that allowed us to sit in, hopefully, air-conditioned offices and make these calls and analyze all of the data remotely without putting any safety implications on staff, because that was one of the biggest hold-up when it came to further oil analysis. So what did we find? And it was a lot of data to comb through, to be honest. We did a lot of correlation between loading, temperature, and everything. But immediately, what we found was that there was a very, very high PD source located on a single termination on a single feeder. So on the right-hand side there, you can see feeder 1, A, B, and C, and feeder 2, A, B, and C. And immediately you can see that feeder 2A has the highest readings, followed by feeder 2C and feeder 1A. So one of the things that we had to get around, we had to analyze in depth, was actually the cross-coupling of signals between the 2 sets of terminations as well as the different phases. So we had to do a lot of analysis work to really narrow down the thanks to the time of flight, that was a lot easier, but it's still, there were times where signals were strong enough to travel between both terminations and hit the sensors. One of the things that was really interesting for us as we were doing this, we spent a lot of time looking at the schematics of the termination, trying to pinpoint where we think the defects could have been forming. And our original point was we believed it may have been on the stress relief cone. And then once we looked at it, what data we were seeing wasn't lining up with how we believed that defect would kind of degrade over time. You can see that on the feeder 2A, we were seeing 46 decibels, very high level, but 9.79 pulses per cycle, which is a lot higher than we were expecting. For the type of defect, we were expecting it to be closer to the number 2 for 2 pulses per cycle, which is the normal bracket for internal void. So having it sit a bit higher made us start to think about, was it degrading in a way that we weren't expecting? And that's something which Brody will talk about a lot once we get to the forensic side of it. But this is what we were physically looking at with the data. So these are the plots that we received back to the Astute monitor, and it's 2-minute data for the amplitude, pulses per cycle, and severity, looking at each of the 3 phases. So you can see the blue line in the top of those 3 diagrams represents feeder 2 phase. And it is relatively consistent. It did go up and down a little bit, which may have been attributed to load, may have been temperature, may have been parts of it thermally expanding inside the CT. We couldn't draw a solid conclusion on what was causing it. But one thing we did note over the entire monitoring period is that we didn't see a huge trending up or down of the amplitude of the signal. It remained very consistent, which was good, but it also made it very difficult for us to decide, is it getting better or worse looking from that? We did notice that the discharge rate did have a slight trend upwards, but what we really used to analyze this was the phase resolve patterns. But if you look over on the right of the plots, you can see how significantly all of the amplitudes of this feeder dropped the second that the asset was de-energized. And that gave us a lot of confidence that we had located it to the right asset, because if we de-energized and they didn't all disappear, then we probably would have made the wrong call. So how we did this in the office is we did the phase plot analysis. So every 2-minute data set that you saw in that plot over the month gave us a full phase resolve pattern that we could analyze. And I'm not going to go through full phase plot analysis today. There's a lot of tutorials we've done on how to analyze these. But the crux of it is you're looking for clusters of activity, specifically with 180-degree separation on the sine wave. So you can see in the top left, we do have a distinct cluster on the left-hand side of about the 90-degree mark, and a little bit of activity on its 180-degree counterpart. But what was more interesting to us is, as time moved on, these clusters evolved. You can see them developing that kind of internal wave that we often associate with internal void type PD. But again, this data wasn't exactly what we were expecting from our initial thoughts of where the defect would be occurring, because there isn't that perfect second cluster 180 degrees separated. So there could be a number of reasons for this, and we talked about this a lot when we were doing the analysis. It could have been due to such high level signals, we were only picking up the right peaks. But one of our leading theories is there is a phenomenon in PD that as you do have discharge occurring either very close to the conductor on the live portion or on the right outside of the insulation on the earth portion, you will start to get a lopsided effect in your phase resolve patterns. And when we start to look at where the defect is, it is quite possible that that was correct. But you can see in the last picture, the second that we de-energized it, the phase resolved activity disappears. There is still some activity which could be coming from nearby assets or other things, but the big sets of clusters that we were really worried about that were changing over time disappeared. And that's what we worked quite closely with Brody and the team on as we were trending these over time, and we ended up getting some great results. So from the partial discharge point of view, that's how we accomplished it. And that's how we all worked together to make sure. We did have a lot of alarms set to make sure if things were trending up, we knew immediately. But in the end, the calls that we made and the information that we passed on to Powerlink for them to make their decisions was primarily based around the phase plot analysis. So I'll pass over to Brody now for the fun part, which is what did we find?
So I'm going to chat about the failure analysis and the methods we used to determine the fault evolution of the asset, this being a 275 cable termination. But EA technology provided excellent data for us to analyze together and make those dynamic making decisions. So it's data that we get immediately through the system, and it allows us to respond fairly quickly to evolving faults. We're lucky, as Thomas mentioned, the fault evolution was quite slow in this particular case, but it was excellent to know how fast things were operating and those operational project decisions behind followed. So the failure analysis combined laboratory testing and the dissection with an aim to identify the source of the partial discharge inside this oil-filled termination. So this was an XLP cable in a oil-filled termination, which was a synthetic silicon oil. The testing and investigation included dissolved gas analysis, which is quite routine, external visual inspection, and then we went into further subcomponents as that dissection went forward. We performed Fourier transform in spectrometry, scanning electron microscope and energy dispersive X-ray, as well as the typical stereo microscope. This testing was performed independently by the University of Queensland Materials Investigation team, and we'll show some of that data as we progress. So the external inspection, as Thomas mentioned, we were mainly looking for an internal evolution of the fault, so we didn't expect to see a lot on the external of the cable termination. So the outer porcelain was, yes, slightly polluted, as you will get from assets that are outdoors. No signs of oil leaks were noted, and no external tracking or heating localized on the cable termination. The internal inspection found a large number of contaminants, so sediment in the oil, which we'll discuss a little bit later in the presentation, and sediment built up on the XLPE. But as for PD activity outside the termination, nothing was noted other than general effects of corona and pollution. So the internal inspection, I won't go into how cable terminations are designed, but essentially, as you look at the cable termination, there's an outer porcelain in this particular case installation that has a silicon internal oil, and then the cable termination itself from the conductor is chamfered outwards onto the XLPE, and as you get towards the lower end of the termination, there is a semicon stress cone which helps grade the voltage that needs to decay as we progress further into the termination. As you can see, there's a clear identified contamination region available on that photo there. So that's looking at the very top part of the cable where it's chamfered down. So on that chamfered section is where most of the contamination is noted. So looking further into the dissolved gas analysis. So those that have been around HV assets know that dissolved gas analysis is one of those proven techniques of identifying what occurs within oil-filled equipment. So samples were taken periodically over its operating life after we found the initial acetylene buildup, and we can see the trend of it. Some gases trend down, some gases trend up in this particular case, but it is important to note that there were periods of de-energization throughout these samples. So that accounts for, say, the CH4, the methane degrading at the time. Sample 3 was taken significantly after the asset was removed from service. But we can see the general heating gases there are elevated of more than what we would expect. So the ethane, the ethylene, the hydrogen, and the acetylene in the oil. And we can see the acetylene trending upwards over time. So the main way dissolved gas analysis within Powerlink is analysed is the Duval triangles. There's several other methods of ratios in gas that help identify what could be the probable cause. With this particular asset, Duval triangle 3 was first used, and then a separate triangle for silicon synthetic oils was used in further analysis. What we can see there is the ratios clearly point to high energy internal arcing and discharge, commonly referred to as PD. So we were fairly confident that there was partial discharge occurring in the asset. The DGA combined with the phase plot analysis and the pulses per cycle and the information and support we got from EA, there was a high level of confidence that we had issues with inside these HV terminations. So getting more into the complexity of the investigation, Fourier transform infrared spectrometry is an analysis technique that identifies chemical components across the insulation medium, and specifically we're looking at the XLPE. So 3 main samples were taken: the contaminated region, so the area of dark pollution, the clean region, and then we took a small sliver of XLPE off the cable at 0.2 millimeters thick, and measured the underside of that. And that was to see what had penetrated the surface of the XLPE. We can see a generic overlay of silicon on the profiles that we're looking at. And then that can be expected from the silicon oil embedded in the termination. What we can see is an overlay of methylene, silicon byproducts, and small amounts of carbon and oxygen. So what we can say from these is that while not a definitive explanation, there are signs of abnormal electrical discharge within the termination. Moving forward, scanning electron microscope. A solvent wash was used over the XLPE to try and remove some of those contaminants, but silicon, especially silicon oil on XLPE, is incredibly hard to remove. So you do see that silicon layer across the SEM. Nothing was particularly noted from the scanning electron microscope. So we looked further into what kind of chemical components we could see further on, and that's where the energy dispersive X-ray comes in. So we can see on the right-hand side there, this is just two regions, the contaminated region and the clean region we're comparing. You can see the large spike where silicon resonates from the silicon oil, and then you can see two smaller spikes of carbon and oxygen. You'll notice there's not too much difference between the contaminated region and the clean region. So we didn't get an overall confidence from this particular technique that it was definitely partial discharge, but the Fourier transform analysis combined with the pulses and the patterns, as well as the dissolved gas analysis, really gave us that confidence that partial discharge was occurring. This is where the analysis gets really interesting, well, from my point of view anyway, is that the stereo microscope, so this was the last ditch effort to try and find some forensic evidence that could lead us to a conclusive conclusion. So stereo microscope is your typical microscope looking at the very top surface of the XLPE. So again, 3 of those samples were looked at through the microscope: the contaminated region, the clean region, and the underside sliver. The contaminated region was far more coarse than we would have expected, and definitely far more coarse than the surrounding XLPE. So we hypothesized that the contaminated region associated with that chamfer had elevated levels of temperature, being also at the oil boundary, and that was high levels of methane, indicates that the DGA. The clean region, while a little bit more coarse, was significantly smoother. Several research through IEEE and CGRE and plenty of papers that suggest if the XLPE is coarse, like you would see in this, then pockets of partial discharge can occur. But as Thomas alluded to earlier, it wasn't the typical void type partial discharge that we expected. This was more of a surface distributed partial discharge area, and that accounted for the higher pulses per cycle.
Yeah. So what we ended up hypothesizing is that rather than a single discharge site within the coarser regions going around the entire XLPE layer, it was more of multiple lower level discharges which were discharging out to the oil rather than within and degrading the insulation itself.
Yeah.
Over time it was degrading a little bit, but rather than it was more contaminating and breaking down the oil insulation rather than the XLPE within itself. And that would explain, similar to our phase resolve patterns, why it was very lopsided, because it's on the right outside of that insulation layer, as far from the live component as it could get. So it was interesting to see this type of data because it was polar opposite to what we were thinking before we broke it down, but it did line up with a lot of our data, because the higher pulse rate can also be somewhat explained by the fact it was multiple discharge sites. It wasn't one point discharging a set amount, it was multiple points discharging all over a select region, which is quite interesting once you start to correlate it backwards.
Absolutely. And that typical discharge into oil will form the wart-like texture of the contaminated region. It's an implied photo. So everything kind of aligned with that distributed partial discharge source at the chamfered region due to the coarse nature of the XLPE preparation. So we'll go into the summary.
Yeah.
So the summary of findings with the failure analysis is, as we just spoke about, PD was likely formed around that coarse surface of the chamfered region, just below the oil level. This has resulted in localized heating and left that discoloration on the XLPE insulation. The PD source can be thought of as that distributed signal rather than a specific void type partial discharge that you would commonly see in other HV assets, such as current transformers, voltage transformers, or power transformers. So it was excellent for us to find that different style of partial discharge and something to be aware of when monitoring oil-filled assets, especially with XLPE insulation. It was difficult to determine the criticality to this failure. However, reconditioning of the termination would likely have been ineffective had we not proceeded with the forensic investigation coupled with that online monitoring data. So if we hadn't known that that surface was significantly coarse, reconditioning would likely put us back in the same position.
Because it's one of the things that when Brody and I did the breakdown and everything, what we were expecting to see was quite a large discharge site due to the amount of energy given off in partial discharge signals. And when we broke it down, we couldn't easily tell that there was significant, that it was rough or there could have been discharge around those points. So if you were to clean up the termination, put it back in service, you wouldn't have fixed anything. You may have been putting your oil in, you get better results, but over time it would just begin to degrade further and further. And without forensic analysis, we never would have known. Not something we could easily tell with the human eye. So from the other side of things and the transition of permanent monitoring into outdoor yards, we learned a huge amount. And one of the things that we learned and can agree on with Powerlink is that it's a really good method for mitigating the risk of partial discharge in transmission level assets. The risk of failure, the risk of safety to surrounding people. It was a really effective tool that we were able to work with Powerlink to manage this asset. That could have been, or that was still quite difficult to manage as a project, but could have been a lot worse. What I think your team's got the most out is the 24/7 access to data. The fact that if people did need to go in, or if you did need to justify some decisions, you could talk to us, you had your own access to all the portals, and you could make real-time decisions. It wasn't, we need to send someone on site, we need to do a risk analysis for entering. It was, this is what we are seeing now, how can we use that to plan safe and other forms of testing.
And that trending over time really helped us analyze and really risk assess the operational issues that occur in this type of asset.
And I know one of the hardest things that we discussed about is time to failures. And the answer is, how long is a piece of string? But I know it gave us a little bit more confidence to see that it wasn't drastically trending upwards, that it was relatively stable. And when we did start to see that evolution of the phase plots, we could start to put in actions. And we were lucky in a sense that it was long enough for Powerlink to make network adjustments to the point where this could be de-energized without significant network changes. There wasn't really anyone offline due to this. So, yeah. From a pure data analysis point of view, it was quite interesting to, rather than focusing on the pure amplitude of the TEV and what we were seeing, to start to trend the pulses per cycle. And really we focused on the pulses per cycle along with the phase point analysis. And that's from me and my team who worked on this and combed through the data. It's a little bit different to normal because normally we're looking for signals to pop up and do it. But this one seems to be relatively similar the entire time, but just slightly more defects were evolving, which is a telling sign of once you understand where the PD was occurring. And if we did leave this, and we'd love to leave it, but we may have seen over time it go up and up and up, and more sites and everything, until eventually it may have led to failure. But that's always the hardest part. But if anyone does need anything, you can give Brody or I an email, add us on LinkedIn, and we're more than happy to go through the project as a whole. But other than that, thank you all for joining us. I think it's been a really good session. We've had some good questions come through. All of the questions will kind of get a formal answer to you. Some have been answered as we go on. And I would like to say thank you to Brodie and Powerlink for joining us today. It's always good to be able to share this data and have people from the industry come and have a chat with us.
And thanks for the support you provided through the project as well. So,
no, perfect. Right. Thank you very much, everyone. It was great to have everyone here.